Recording.
Okay, so let's move on our last conference of the Congress. We have a pleasure to have with us George Jean. He's a full professor of University of Connecticut in the United States. His research covers a very extensive part of mathematics. He is interested in applied mathematics, stochastic optimization control, and approximation stochastic system theory, numerical method, mathematical biology, and system identification. And today he will give a talk on computational nonlinear filtering, a deep learning approach. So thank you very much for being with us, and you can start.
Thank you very much. You can hear me okay, right?
Right, we
Okay.
hear you
Uh,
well.
to begin with, I want to thank the organizers, especially Anna, Juan, and also Diego for putting together the very, very nice program. I'm very happy, very delighted, and to be part of the celebration. It's great. So, so what I'm going to talk about is computational nonlinear filtering, and it has some connection to the deep filtering, and well, to the learning part. You will see that. So here is the outline of my talk. I will begin with talking about what a nonlinear filter is about. So I realize, many people are working on PDEs, not necessarily in a stochastic PDE or filtering. So I will spend some time talk about the history and the literature and so on and so forth. And then we'll talk about, what um, our approach is and how do we actually solve the problem. Um, I will not prove anything, but I will show some numerical result. I will mention some uh, result, but not the detailed proof. If there is if the time permits, I will try to also give a presentation on the related filtering problem with degeneracy, but it's likely we don't have that much time. So finally, I will end the talk with some further remarks. So, so let me begin. As I said, I'm very happy to be part of the celebration for the seminar, the Congress. Now, let me begin with acknowledge my co-authors of the work, Hongjiang Qian, who was my former student, currently at Auburn University, and he was his first postdoc was at Cornell. And then also my colleague Qing Zhang, we worked together for a very long time. We were both graduate students when we were at Brown. Okay, so let me begin with what nonlinear filtering is about. So here we are given a pair of stochastic differential equations. You have a x, you have y. Both of them depends on some nonlinear function, where here the, the w is a standard Brownian motion, high dimensional. So is the v is also another independent Brownian motion. So x is known as the state, whereas the y is the observation. So we don't know exactly what x is. What we do is we observe y, but we observe y with some noise. So we don't see the true y. We can only, I mean, true x. We can only see partial of x through some function h and some noise. So this is also known as a partial observation. So the problem is as follows. based on the information, I use the script YT. Basically, that means the sigma algebra generated by those y up to the time t. With this, what we want to do is that we want to really estimate what the unknown x is. So let me do a little bit more formulation on this. So we are working with E, which is a complete separable metric space. So X, the state, is a Markov process. And it lives in a space which I denote by D, that is a space of functions that are right continuous with the left-hand limit with certain topology known as Scarhard topology. And we have script A, which is the operator or the elliptic operator. And H is a nonlinear function. Both W and V are independent Brownian motions. And the Y here is our observation. So the YT is, you observe the X through the nonlinear function H and the additive noise V, which is the Brownian motion. And we use the script Y to denote the information up to time t. So this one is a sigma algebra. Now we use pi t to denote the conditional distribution of the state xt given the information up to time t, or the script y. And f is a measurable, Baruch measurable function on the complete separable metric space. And we use the notation pi t parentheses f to denote the conditional expectation, or it's just the integral against the conditional measure. So what the nonlinear filter does is to calculate either the conditional probability or the conditional expectation. So, so here we have something called the innovation process. What that is just another basically Brownian motion. It's the observation minus the pi t. You consider the conditional expectation with respect to the conditional density. So now this is or was really a very active area of research in the 1960s. In 1960s, one of the well-known Kushner's equation was obtained. It is, well, this seminar is about the PDE. The system we are looking at, or the differential equation we are looking at, is actually stochastic partial differential equations. It is a partial differential equation because, as you can see, the following equation. So here, the operator is acting on F. The operator is an elliptic operator. So we do have a stochastic partial differential equation involved in this case. So that was the first equation obtained in the 60s. Now, a few years later, people also look at the problem. Some people thought, by the way, the Kushner's equation is really, the pi t is truly a probability distribution, conditional probability distribution. But they thought maybe if we don't use this probability distribution, but rather use something not normalized, would be easier. So there's another class of stochastic PDE obtained. This stochastic PDE actually now is named the Duncan-Mortensen-Zakai equation. I will say a few words about the origin of this. So this equation is given by the following differential equation. Again, it involves a partial differential operator. So um, I wrote in a more simple way, but if you write it out, you see the PDE part comes out. All right. So so let me give you some literature and the history of this. Now, perhaps one of the first paper published along this line was the paper by Stratonovich in 1960. That was in the Russian journal Theory of Probability and Application. So actually, he used his own calculus known as the Stratonovich integral. So by using that calculus, the integration by part formula still hold. Uh, we all know by nowadays the so-called Ito formula, the integration by parts formula do not hold. So, you know, about a few years later, Kushner published his result. The Kushner's equation appeared in Science Journal of Control. Actually, when he published the paper, he criticized Stratonovich. He said, you know, the Stratanovich's result should have a correction term. Well, the reason for that was that Kushner was using Ito formula, whereas Stratonovich was using his own stochastic calculus or Ito's formula, or Stratonovich integral. Now, a few years later, Albert Shreyev, published the paper in, again, the Russian journal. This time, he used the Ito calculus. During that period of time, essentially, you have some result published in Russia. You will have a similar result published in the West. So here is a similar thing like that, something published in the West, then something published in Russia. Now, during that time, the research in nonlinear filtering was actually very fruitful and very sort of like a hot topics for many people. So, so in 66, Taran Duncan at Stanford actually, um, you know, wrote his thesis. Uh, Basically, that's the starting point of the whatever you call the Duncan-Mortensen-Zakai equation. There's another uh, person, Mortensen, was writing his dissertation in Berkeley. So his paper was published in JOTA, Journal of Optimization Theory and Application. But Tyrone Duncan's paper was never published in the paper form, only appeared in the PhD dissertation. A few years later, Zakai wrote a paper published in the famous German journal. So if you happen to be interested in reading that, you will find at the very beginning of his paper, he mentioned, when I finished the paper, Tom Kallis, who was uh, really the Tyrone Duncan's the PhD dissertation advisor, wrote to Zakai saying, my student also look at the problem. So Zakai actually then said, which of my theorem in proposition so and so or theorem so and so was related to the result of Tyrone Duncan. And he also noticed that the work later of, Mortensen. He also mentioned my result of so and so appeared in the Mortensen's work. So, so that's pretty much like the development of the Kushner's equation and also Duncan-Mortensen-Zakai equation. By the way, Duncan, Mortensen, and Zakai all did their work independently. So later on, people took credit all of them, they put this equation with three names. And uh, by the way, during that period of time, Kushner was working at Brown. So was Maureen Warner. Uh, for those of you working on the area of control theory, you know, one of them has a well-cited textbook in like linear systems, but he was also happened to work at Brown. So, you know, I think because of Harold Kushner gave a talk on nonlinear filters, so he also got interested in. So, so then he wrote this paper on a particular kind of a nonlinear system, which is called, later on, was coined the name Wanham filter, which is really just you have a hidden Markov chain. The Markov chain is not known. You want to, you have an observation to it. You want to estimate that. So he obtained a quite nice result uh, in that regard. Um, all right. So I see there's some chat, but maybe if I miss that, I can answer the question at the end. Maybe Anna can help me out. Now let me continue on the reference part. Um, so later on, there was a paper obtained by written by Tom Kurz and Daniel Okun. Basically, what they say is how do you solve this nonlinear filtering problem, especially the Duncan-Motensen-Sakai equation. So what they said is first find the solution for the unnormalized conditional density or expectation. And then uh, you try to show that is indeed the conditional distribution. So their approach essentially is a martingale problem formulation because, you know, Tom Kurz is an expert on that in that area. So there were, approach by Mark Davis on nonlinear filter and the stochastic flow. Recently, by recently I mean in the 80s, uh, Ruzowski and his former student Lotowski and collaborators used the spectrum approach to treat the nonlinear filter problem. And there are also problems from engineering part. You know, Blum and Barshalom did discrete time hybrid systems. My colleague and friend, Francois Dufour from France, uh, treated Markovian jumps. Also, uh, Costas did the linear recursive least squares state approach. I think he was a student of Mark Davis or or, or Clark. There are also Glerkin's approximation. As you can see, you are treating a infinite dimensional subject. So the idea is perhaps you can do finite dimensional approximation. Now, later on, there was another work by Demora and Doucet in using the so-called interacting particle approach. Uh, so now we ask the question, is this problem really solved? Well, in a way, you get a very celebrated result for the nice equations characterized by the so-called Kushner's equation and the Duncan-Motensen-Sakai equation. But for almost 60 years, uh, how to actually find the actual solution of the problem is not quite solved because of the fact it's infinite dimensional. You have the nice equation. You can say the um, the filtering problem is given by the solution, but how to find the solution is not a simple matter because you have an infinite dimensional problem. So how can you actually do that? It's not so clear. And you run into the trouble of basically is a curse of dimensionality. So the computational issue remain to be very challenging for about 60 years. Now, in our case, we are going to treat the diffusion, but we're also going to add a switching to it. So we are actually treating the switching diffusion. That's another fault of complication. So let me begin with the formulation of the problem we were started looking at. So here we have a finite state Markov chain, which is the alpha. The state space is given by this, and this is the generator associated with that. So we call this a hybrid diffusion because you have the following. You also have a continuous state and a continuous observation, but they are multidimensional subject. So the differential equation or the pair of state and observation equations are given by y and x and y. This should be lowercase y. I changed the notation, but this one didn't change. So the additional difficulties comes about when you treat the switching. So now I'm getting to the second part, which is our deep filter. So our essential or our main objective is to solve this problem numerically. We want to be able to find a scheme which is computable for this, for a long time, no good calculation or algorithm to compute that. So we try to find the algorithm to solve the problem. The way we try to solve that is we are using the idea of a deep neural network. I think from day one, Professor Zuzwa gave a talk on control problem using learning using neural network for that. So here is the same idea like that. We start by looking at that, but we propose an algorithm. Basically, the main thing or the main hurdle we are trying to get through is to try to overcome the difficulty of curse of dimensionality. We want to be able to solve it. So now how we start? We begin with the following system of stochastic differential equations, the one I wrote before. And so then what we do is we numerically solve this because you do have the equations, but you don't know exactly, in the problem to solve this, you don't know exactly what the x is. You want to get the solution using the observation. So we simulated that. How do we simulate that? We use Euler-Maruyama scheme to write down the discrete version of the SDE, which is the following discretized version. Once you have that, then you can show this one is actually a lemma or proposition. We can take a continuous time interpolation of that, say piecewise constant interpolation. Then we can show that the sequence we constructed belong to a function space so that the piecewise constant interpolation converges to the true x, y, and alpha. X is the state, y is the observation, alpha is the switching process. We can also define a continuous interpolation in the following way. In this way, we can then compute, or rather analyze the convergence rate. The convergence rate turns out to be uniformly in T. You take the second moment or the mean square of that. The order eta is actually the step size. So we have the convergence. We also have the Scarhard. We have the convergence. We also have the convergence rate. Now, if we use the so-called Scarhart representation, basically we are saying in one space you have a weak convergence, then you lift that to a higher space or to another space, you can show that converges in the sense of with probability one. But that's, I don't really want to say too much about that part. So now, then what we do is that how we implement that by using, how do we use the neural network to treat the problem? Well, we do the following. We generated those xn and yn, then we treat xn as a function of the observation yn, y from 0 to yn. And then we use this thing, use the state and the observation pair, we construct the solution. Well, I will say a few more about that, but basically the output of that is going to be, it depends on what mapping you are using. So we are using the so-called rectified linear activation function for this. So, so basically we use Euler-Maruyama scheme to generate Monte Carlo samples. We use the samples to train a deep neural network. And then we obtain the optimized weight parameter. And then we feed forward another set of Monte Carlo samples for our model to get a so-called deep neural network using optimization, optimize the weighting parameter. So finally, the calculated output, the DNN, deep neural network output, is what we call deep filter. So the well, this is the technical part. Because I don't do the proof here, so I think I can skip that part. Well, another thing we want to mention that is something new, even for a learning related thing. There was once a colleague, Salia, who is doing mathematical finance. He asked me a question about, what can you do for the learning rate? For people doing learning, normally they use a constant learning rate. The point is, can you adaptively or construct some way so that the learning rate will be much better, can improve in each iteration? So in our algorithm, we actually also include adaptive learning rate for this. So instead of just one fixed constant row, we generate a sequence of that, trying to find the better improved learning rate. So this really corresponding to, you get two things. Theta is the parameter we want to estimate. We also generate a rho, whereas rho is a sequence of the learning rate. So here I want to mention one thing. By epoch, we mean the number of passes of the entire training data set going through. So once I have that, I have two recursions to have. One of them is the recursion for the parameter theta, whereas the other recursion is for the adaptive rate, the learning rate. So here, as you can see, I wrote two levels. One is for NL, the other one is K1, K plus 1, K, and so on and so forth. So you will see that in a moment what I meant by that. So maybe we can ignore the details for the this illustration. For those of you who are interested in, you can look at the paper I mentioned. One of them is a basically non-technical version appeared in the SIM News. That one you can see how you can actually basically it's illustration of the idea rather than going through all the technical details. So here I can say a few more about the whole idea or the flow chart if you want. So start from n equal to 0. I'm using a step size rho 0, and then we run through the calculation of those theta. So this is the one level doing this. After you've done this calculation, you update your learning step size rho 0. So from rho 0, you get a rho 1. And starting from rho 1, you do another level updating for the parameter theta. And then you go to the next level, n equal to 2, and you update rho 2. And finally, you get to n tilde or something like this. So this is just the demonstration of that. Um, all right. So now in this process, we also have this, uh, algorithm. Because of the time constraint, I think I will skip that. And as well as this deep learning, basically just tell you, which way you go first. All right. So I had a picture. I don't know why I no longer have it here. I had a picture. So basically, what is the theta? So you start from the first level. You have a number of a node. Then you take a linear combination of those nodes. You get to the one node over the next one. And then once you get to the next one, um, uh, then well, we are using the one, in each level, you don't have a cross uh, thing, but you just, you know, just use, just, taking the linear combination of this. Once you take the linear combination, you are also added something which people in learning call that the bias. You have the parameter which we call that weight, and also the bias. This together give you the next level. So you are uh, uh, going to go through that. And so now, now let me just mention, if the parameter or the learning rate is actually a constant, you can get a ordinary differential equation. You can average out that to average out the noise. Remember, the learning rate is also through a stochastic grading algorithm. So you get this, this thing that tells you roughly uh, uh, if we shift this, if we take a long time, this rho epsilon or the interpolated process will converge weakly to a rho star, where rho star is the optimal learning rate. So we can also analyze the convergence rate by using the uh, a Lyapunov type of function. We can obtain the rate of convergence in the following way. Essentially, it's something like this. The mean square error of this turns out to be something like uh, the second moment or mean square error is of the order of rho n, uh, this. So maybe let me just mention some numerical result. I don't know. I think it looks like I lost some slides in this process. If I get a chance, I'll show you by looking at another file later for that part. So let me look at some example. The first example is a two-dimensional system. The second example is a higher order. It's a six-dimension thing. So we are using 4 layers for each of the thing. The computation for the first example, the layers are 30, for the number of neurons are 32, 16, 8, and 8. For the second one is 128, 64, 32, and 8. Okay, so the first example is this. Normally, if you try to do filtering, whenever you have a sine and a cosine function involved, it's hard because that involves this kind of changing thing. And you also have the Brownian motion involved. But here, the rest of the parameters are, or the sigma, g, and the others are given here. So you can go ahead and do a calculation like this. Then uh, that shows for the first graph shows the mean square loss function or the cost function we are looking at. The second one demonstrates the adaptive learning rate. If your learning rate start to be low, it will go up and eventually stabilize at some point. If your initial learning rate is high, it will the adaptive thing will let it down. And if it's somewhere here, you follow this. So that gives you an idea about that. Um, so one of the things is that we are interested in the so-called relative error or relative efficiency. So here that tells you the relative error corresponding to different learning rate. And those are the computation result for this. So generally speaking, it follows this pretty well. Now, the second example coming from uh, people are doing some calculation for tracking a flying object. So here is actually six-dimensional thing. So you see the h function has something to do with like a distance, whereas here you also have the angle involved and some other variables. So you go through the calculation. So here that shows the loss function. Here is the path of the adaptive learning rate. You see, again, if it's too low, initially it will go up and stabilize at some point. Likewise here, and so on and so forth. So here is a calculation of the relative um, error because it's a much more nonlinear. The rate is slightly lower than the previous case. So those are showing the six-dimensional uh, thing for the different component. So here I'm showing another picture. This picture, the function we are looking at is not in the truly traditional nonlinear filtering view. You don't have the observation, you don't have the state and the observation, you just have one observation equation, but it's one-dimensional. So the calculation turns out to be very good, and you can obtain the result uh, relatively easily. Uh, I think I will have to skip the part for the for the degenerate part. Let me mention the result for linear filtering. For linear filtering, you have the well-known common filter associated with that. So you would ask the question, how is the deep filter compared to the common filter? To the For the common filter, normally you need something to get it started. That's something called a nominal pass or nominal, thing. So here, when you do that, you need to assume the nominal filter to be of this form. By the way, I didn't write down the corresponding differential equation, but rather I wrote down the discrete version of that. Likewise, I wrote down the discrete version for the actual model. So what we found is that normally the common filter is highly related to the, to the uh, nominal uh, nominal pass, but the deep filter is not so sensitive to the with respect to the nominal path. So in a way, um, even if you assume the model or the nominal model is not very accurate, it's not a problem. We can still obtain good calculation results. That's the upshot of that. I think I'll skip this part and make some further remarks. Now, if time permit, I will go back. I don't know why I have a few slides disappeared. So I'll try to find that and show you what I mean by the the uh, the linear combination or the filtering part. So so now for us, the important thing is to improve the accuracy of the calculation. So for the talk, the Markov chain here is not hidden. We assume that is known. We did the case for hidden Markov chain as well. If you have both the Markov chain being hidden, also the perturbation of the Brownian motion term, then the accuracy actually deteriorates. So the one problem is how do you actually improve this? This is a good question for this. And basically how we make it more efficient. Also, there's another one is the related system identification problem we are working on. So if you'd like to see more details, I would suggest if you want to see the technical proof that's in the IEEE transaction on automatic control. But in the SAM news, you will see the main ideas without proof or uh, without the technical details. So with that said, let me say I'm really happy to be part of the celebration, and I want to again thank the organizers for the invitation and congratulations to you, and thank you all very much.
Thank you very much.
Should I
So,
stop sharing?
as you want.
Well,
Yes, let's just wait for if there are some questions, and
sure.
you want probably you would like to show something in your slides.
Yeah,
So
yeah.
yes, keep sharing, please, for the moment of the questions. So are there any questions or comments? Yes, as usual, you can use the chat or microphone. So in the chat, don't worry, there were some organization messages, just not related to your talk.
Oh, okay.
Okay, no, so you were wondering what it was on the chat.
Right, right. I wasn't sure if those are questions.
No, 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 no. It was just some organization
So what
for.
I can do is I could do the following. I could uh, put together the few pages missing and
Yes, please.
send to you again later. So if you want to, you can post that one. That would be more complete.
I just would like to ask you a question, a curiosity, for the numerical experience. How did you decide the structure of neural network? So
Oh,
how do you choose the layers and
yeah,
the hidden layers and the neurons in each layer?
yeah. So actually, those are in the missing few slides. So I don't know. I did this, maybe because I came back last night, as I told you, I was after
Yeah.
midnight, so I'm a little bit disoriented, so I lost a few pages for that.
So
Um,
I don't know. You want to look for the lot
Yeah.
slides, or you
Sure,
just
sure,
in NASA in abstract way? So
sure, sure.
we,
So let me stop here and then try to look for another slide. How about that? So now let's see. Finish. Oh.
estaba buscando unas transparencias que quería mostrar, que está relacionado con la pregunta que le he hecho.
Now let me try to share my
O sea,
screen again.
okay. Ujú.
So um, where can you see it?
Yeah. Ujú.
So yeah,
Yeah.
I'm sorry. Last night when I come back was too late. So
Yeah, yeah. Don't
so
worry.
so you see, you have some input layers, you
Ujú.
have some hidden layers, and you have output layers.
Yeah.
So uh, we said we are using direct or deep neural network. So there's no uh, no interaction in this layer. There's no connection. You only go this way. So how is the thing? Suppose you have the first layer right here, then you take a linear
Ujú.
combination of those. So here, those are the weight added. And then you get to the next level. And then you are using so-called activation function. This part is what we call the weight. This part is the bias. So you take the linear combination at the bias, and then you use the activation function. So you can write it in the following way. Well, this is a large dimensional thing, really. Uh, but the activation function we basically make the approximation nonlinear. So
Ujú.
this is how the the uh, the layers and the things are related. So later on, we call here I use the W to denote the weight. Later on, we call those W, B, theta, which are the optimal parameter we are searching for. We are using uh, least square, mean square error to do the
Ujú.
optimization to get the optimal parameter. So in this way, we are doing this level by level, many computation. So
Yeah.
repeated. So it's a large dimensional computation involved. But the whole thing is that, previously, for, as I said, 60 years or so, there's really no computational, easily usable computational algorithm usable to solve the nonlinear filtering problem. Because SPD with a high dimension, infinite dimensional problem is curse of dimensionality. But this one, we really convert the infinite dimensional problem into a finite dimensional setting so you can solve it in a way. So it becomes a solvable, basically.
Okay.
So
Okay.
I hope that illustrate. I don't know why this a few slides disappeared, but I mean, last night it was too late for me.
Yeah. Yeah.
So
So now,
yeah,
yeah.
yeah, we
Okay.
were, initially when Wang contacted me, I said I couldn't do it on the 8th or 7th because I need to go to Washington, D.C. for NSF report. So we were doing a report over there. And after I finished, I came back last night. So,
Okay.
so what I can do is I can edit the few slices and then send you the complete slides later tonight.
Okay, so thank you very much for your talk. Are there other questions? Okay, so we thank you again for this very nice talk.
Thank
Uh,